Hello everyone, this is Professor He. Nice to see you again. The topic of this task is about the third law and the absolute entropy. The property of entropy plays an important part in quantitative evaluations using the second law of thermodynamics. When reacting systems are under consideration, the same problem arises for entropy as for enthalpy and internal energy. A common datum must be used to assign entropy values for each substance involved in the reaction. This is accomplished using the third law of thermodynamics and the absolute entropy concept. The molecules of a substance in solid phase continually accelerates, creating an uncertainty about their position. These accelerations, however, fade as the temperature is decreased, and the molecules supposedly become motionless and absolute zero. This represents a state of ultimate molecular order. Therefore, the entropy of a pure crystalline substance at absolute zero temperature is zero, since there is no uncertainty about the state of the molecules at that instant. This statement is known as the third law of thermodynamics. Substances not having a pure crystalline structure and absolute zero have a non-zero value of entropy and absolute zero. The experimental evidence on which the third law is based is obtained primarily from studies of chemical reactions at low temperatures and specific heat measurements and temperatures approaching absolute zero. The third law of thermodynamics provides an absolute reference point for the determination of entropy. The entropy determined relative to this point is called absolute entropy, and it is extremely useful in the thermodynamic analysis of chemical reactions. Entropies can be viewed as a measure of molecular disorder or molecular randomness. As the system becomes more disordered, the position of the molecules becomes less predictable, and the entropy increases. Thus, it's not surprising that the entropy of a substance is lowest in the solid phase and highest in the gas phase. In the solid phase, the molecules of a substance continually oscillate about their equilibrium positions, but they cannot move relative to each other, and their position at any instant can be predicted with good certainty. In the gas phase, however, the molecules move about at random, collide with each other, and change direction, making it extremely difficult to predict accurately the microscopic state of a system at any instant. Associated with this molecular chaos is a high value of entropy. When viewed microscopically from a statistical thermodynamic point of view, an isolated system that appears to be at a state of equilibrium actually exhibits a high level of activity because of the continual motion of the molecules. To each state of macroscopic equilibrium, there corresponds a large number of molecular microscopic states or molecular configurations. Boltzmann first hypothesized that the entropy of a system at a specified macrostate is related to the total number of possible relevant microstates of that system, W. This thought was formulated later by Planck using a constant K with the entropy unit of joule per Kelvin, named after Boltzmann, as S equals K ln W, which is known as the Boltzmann relation. Notice that the entropy of a substance that is not pure crystalline is not zero and absolute zero temperature. This is because more than one molecular configuration exists for such substances, which introduces some uncertainty about the microscopic state of the substances. Molecules in the gas phase possesses a considerable amount of kinetic energy. However, we know that no matter how large their kinetic energies are, the gas molecules do not rotate a pendule wheel inserted into the container and produce work. This is because the gas molecules and the energy they possess are disorganized. Probably the number of molecules trying to rotate the wheel in one direction at any instant is equal to the number of molecules that are trying to rotate it in the opposite direction, causing the wheel to remain motionless. Therefore, we cannot extract any useful work directly from disorganized energy. Okay, that's all for this task. Thank you very much, and see you next time.